Bam. All right. We're actually broadcasting, so this is fun. All right, welcome to Chalk Talk 381. We're going to be doing a programming Chalk Talk today. We're assuming a certain amount of familiarity with Python and Numpy, but I know that some of this stuff will be new to some people in here. So if I do something in Python or Numpy that either is wrong, because I'm not all that expert on any of this stuff, or you say, hey, you know, you can do this better, tell me about it, because I like learning about this stuff as well. But if you have any questions about Python or Numpy or any of the things that I'm doing, please stop. If you have questions, other people might have them as well. Second, we're going to be talking about Theano. Theano is it's a relatively new package. It's I think it was actually in the 2000s developed. Developed by these faculty people to do machine language or machine learning kind of stuff. It's really focused on machine learning. But at its core, it is a computer algebra system that can basically figure out what the math you've typed into, produce C code, compile it, and then run it all within the framework of Python. And you're going to look at this and you're going to go, wait, no, this is impossible. But it is, because we live in the future. So this is going to be fun stuff. So I'm now going to switch over, and you're not going to see me anymore. We're going to start screen sharing. And I'll do that. I'm going to do it on YouTube first. Boop. Google Hangouts. Okay. So let me just double check that. Yes. And I'm going to present to everyone. There we go. So now this is the window. And now I'm going to screen share with you guys. Bloop. And then I'm going to choose our input here. Ha ha ha. Things are working out. And this is, let's see, I should, what? Ignore. This is my calendar. Ignore. Of course.
Oh.
What the hell is going on? Screw it. Okay.
Is this why you're flying down there?
It's because I'm that. So let's see. I want to make this bigger, so I'm going to turn off. I don't need to see the bookmarks. Don't enter full screen. That's what I want. There we go. All right. And we can make it bigger. So Control plus, Option plus. Bing, bing, bing. There we go. And it's about as big as it's going to get without. I wonder if there's a way to, ooh, toggle hair. Yeah. Toggle toolbar. Yeah, we're not going to be doing anything. There we go. Woohoo. All right. So now, Theano. So first of all, like I said, Theano is a algebra system. It's a symbolic algebra system, and the guys on the Theano website described it. If you're familiar with Mathematica and MATLAB, even if you're not, let's talk about Mathematica and MATLAB. MATLAB was developed to be really good at dealing with matrices and vectors and linear algebra and stuff. So MATLAB, you can create a matrix, you can manipulate it, you can take rows of the matrix, you can do all sorts of cool things with it really easily. Mathematica, on the other hand, was built as a symbolic math problem package. And as these two packages sort of grew, they kind of started merging. Like you can do linear algebra stuff in Mathematica, and you can do symbolic math in MATLAB, but at their hearts, MATLAB is a linear algebra package that lets you do fast things with matrices and vectors and stuff. And Mathematica is this cool mathematical processing language where you can type in an equation and it understands the equation. It knows that you just typed in x squared equals y squared plus z squared. It has a sense of what that means. And you can ask it to figure out the derivative of that equation or integrate it over a range or do all sorts of cool stuff or simplify it. Mathematica is awesome. You type in a big complicated equation and you type simplify, and Mathematica will do all sorts of arrangement where it'll say, okay, this equation looks complicated, but really it's just x plus 2. It'll figure that out for you. Theano sort of sits in the middle. So what Theano does is it says, well, first of all, NumPy was built to be a Python version of MATLAB, right? It's something to deal with matrices and vectors and make it fast and easy to use. Then there is also SymPy. SymPy is a package we really haven't talked about in this thing, which is cool. It's a more mathematical kind of manipulation of equations and stuff. And Theano said, let's try to combo these two things together, because we're doing a lot of this stuff in machine learning, where we're dealing with these huge matrices, but we're also doing some really interesting math on this. So why couldn't we take some of that symbolic math processing, combo it with some really fast matrix and vector operations, and see if we can't get it to work? And that's what this program is. Now, the cool thing about this is that it is all in Python, and we're going to go through a little bit of an example to show you the coolness that's happening here. So in this first example, we're going to start out with what you need to run this thing. And at Digital Domain, and basically anywhere where you have Theano installed, first of all, you should probably always import NumPy, because NumPy is like the ground standard for math and stuff. This is how we're going to use NumPy to create our matrices and then feed them into the Theano framework. You could just say import Theano, and there's I deliberately don't do from Theano import or import star so that it all becomes in the namespace that you're in. I'm just saying import Theano. So anytime I want to use a Theano function, I have to say Theano.function, just so you know what is part of Theano and not. Except I do this, and this is a standard thing in Theano land, where you say import Theano tensor as T. Now remember what a tensor is. A tensor is just sort of a general purpose matrix, right? A tensor is this mathematical framework that says, well, you could have an n-dimensional matrix with these kind of things. It's just a very generic way of representing a matrix. The number 2 is a tensor. A 2x2 matrix is a tensor. A 3x17x45 matrix is a tensor. So the tensors are just a big thing that represents data in sort of a matrixy form. All right, so we are going to, whenever we want to use a tensor, and remember, representing a piece of data in there, we're going to use the letter T. That's a fairly standard thing in Theano land. All right, so how do you use this? Well, the first thing you do is you say, well, what I'm going to do is I'm going to create a mathematical variable called x. And I specifically called it a mathematical variable because x is now a Theano tensor. It is a thing that doesn't actually have a value. And you can, if you wanted to, you could take and do that. But variables, there's the variable representation in Python, which is x. But Theano really wants you to name the variables. You don't have to, but it really helps to debug things if you do name them. And so you see a lot of things where you say, I'm going to create the variable x, which is a Python variable, which is a tensor, and I'm going to give it the name x, so that when Theano works, it'll say, hey, you've got a problem with x. Well, inside Theano's brain, it's actually looking at this little string thing. And so it can get a little confusing if you create a variable in Python called x and call it something else inside Theano's brain. So that's just sort of the convention of how this thing is set up. So we're going to create, and it's a scalar, and it's a double. Theano is a highly typed language. So there's integers and floats and different sizes of integers and different sizes of floats and doubles. And in fact, it becomes really important. Like right now we're creating a double. If I wanted to run this on the GPU, which you can, which is awesome, you have to use float 32 at this time. Any other thing, the double support is coming with the latest and greatest GPUs that are out there. But when Theano is built, you have to use float 32 if you want this thing to run on the GPU. If you don't use float 32, if you use double, this thing will only run on the CPU, but it will run in parallel on the CPU, so that's kind of cool too. Okay, so we're going to create the mathematical variable x, then we're going to create the mathematical variable y, pretty straightforward, and then we're going to create a little math. We're going to say z is equal to x plus y. I don't have to put t dot whatever in there because now Python knows what the types of these things are, and so we know what z will be. And so this is like a little equation, right? X plus y equals z. And of course, you've written code before, and you're like, well, yeah, but inside Theano, that is just an equation. It's just sitting out there saying that if you add x and you add to y, you're going to create z. All right? So nothing has actually been done. There is no, z does not have a value other than it is x plus y. It doesn't have the value of 2, for instance. We haven't executed anything at this point. We're just describing some math. All right? Now, we haven't executed anything yet either. We're going to get down to here and we're going to say, okay, I'm going to actually create a function. I'm going to create something that we can execute. In fact, if I set x equal to 2, I think I get an actual error. I haven't actually tried that because you can't. X is just this sort of mathematical variable. In this thing, you're saying, okay, I want to create an actual function that I can execute. And my function is going to have 2 inputs. Variable y, and that matters. The values that you get me are going to be put into x and put into y, and then I will return the value z. So the parameters for this thing, and we'll see some more examples of this. This is a list of the inputs to your function, and this is the output to your function, which can also be a list, which you'll see in just a moment. Okay, so let's do that. I'm going to hit Shift Return, because this is all a Jupyter thing. I'm actually running code. If you guys haven't seen Jupyter before, this is a website. This is actually, an HTTP thing running off my machine. But underneath this, there is a kernel of Python running. So when I hit Shift Return, that actually ran some Python at that point. I will make this page available on a GitHub account afterwards, and we can continue to update it. But you'll notice if you go to the Theano documentation, I haven't really strayed very much from the Theano documentation. This is sort of a live telling of what they've done. So you don't really need this page to get into it, but I will because it's kind of nice. So now, to actually run this function, you run it like a normal everyday Python code, piece of code. So I have f here, and I'm actually going to call it. And if I hit Shift Return, bloop, I get an array of 5 coming out there. So it actually ran that executable function. And so far you're going, really, is that all there is? That's kind of weird. But something happened when I pressed Shift Return there. And in fact, because it's so fast, you didn't actually see it. When Theano realized that I was going to execute f for the first time, it said, holy smokes, all I know is that I have this mathematical equation that I've just built there. I really don't know how to run it. Or actually, I do know how to run it, but I want to make sure I run it fast. So Theano stopped. We left Python, and it created a little teeny piece of C code that represented what the math was in that thing that I created there. And it created that C code really efficiently. Theano has been tuned because it's been built for some machine learning applications to do it as parallel as possible. And we'll see some examples of that later. So when I hit Shift Return, the compiler actually, and you can see this when you first start up Theano. I've had this running on my machine. You'll feel this little pause where Theano goes, what? And then you can feel the C++ compiler actually running in the background. And at the end of it, it's created a little bit of C code. Then it feeds the C code the 2 input values, and the C code returns the values that it's supposed to Theano, and then it presents it in the Python. So underneath this, I just created a little piece of C, which is cool. All right, and this is the whole thing with Theano. That C is as parallelized as it can be, according to Theano, and Theano can parallelize the crap out of stuff. And not only that, I can supply a switch to Theano to say, when you're compiling this, don't compile it just for the CPU, compile it for the GPU. And Theano will switch over and use CUDA and the NVIDIA compiler to actually compile this for the GPU, and it will try as hard as it can to make it as optimal for the GPU as possible. And all you have to do is say, please compile it for the GPU. You don't have to know GPU programming at all. And all of a sudden, Theano will start shoving this stuff onto the GPU for you. Now, you have to know GPU programming in terms of transferring data back and forth, in terms of making this run as fast as possible. but it happens all automatically for you, which is really, really cool. All right, so now I'm going to do another kind of example. Okay, here I'm basically running f, right? And it's just like a procedure call, right? It's a function call. But one of the cool things about this is that, you know, f is executing this math stuff for us. And f, this is sort of another way of looking at this. There's this thing, this whole movement in computer programming called functional programming. And I want to think about what I've done. I've created in a typical Python function or a C++ procedure or something like that. You call a procedure and stuff gets executed, right? You get a piece of code that actually gets run. Well, that's neat. You can do whatever you want inside that piece of code. That piece of code can have state. It can know what it was, what things were going on the last time it ran, or it can read stuff from disk and can do all sorts of stuff. But this thing is a little different. What this is a function. It says, I'm going to take your inputs and transform them somehow. I'm going to take these inputs and do a mathematical transformation on them and spit this out. And I'm not really going to have any internal state. I'm just going to do whatever this function and this transformation on input to output. And that's kind of cool. It's actually a neat way of starting to think about this because you can chain these things together. So before we get to that, a little bit of details about what just happened up there. The variable that I created, the x, if you type, what you get is a tensor variable. It says that all these things, all the variables that are Theano tensors are just tensor variables. But they do actually have a type. Like I said, Theano is a highly typed language. And so if you ask for the property on x called type, it will return that this is a tensor of float 64 because we created it with a double, and it represents a scalar. You can have floats and matrices and floats and vectors and all sorts of stuff, but this is basically a description of the data that's being stored there. And like I said, that name travels along with it. So the fact that this variable is called x and it has a name of x is actually kind of disconnected. It's a nice coincidence that it is there, but the name of the variable is set by that little string that you give it. Yeah.
Did that type actually get defined?
The type got defined right there. Boop, D-scalar.
Oh, right.
So there's a D-scalar, there's an F-scalar, there's an F32 scalar, there's an I-scalar, and in fact, there's a huge list of types that you can possibly create. The default scalar is, if you just type t.scalar, you get a float scalar, I believe. Yeah.
So does that mean that the tensor's data type is a 64-bit scalar, or that it can be a rectangular array in any number of dimensions of scalars, or
it has to be a scalar. So
that tensor is just one
value. It has to be a scalar value. But the neat thing is, when you create matrices, you don't specify their size. So this thing is flexible, but it needs to know whether it's a one-dimensional or a zero-dimensional tensor, or a one-dimensional tensor, or a two-dimensional tensor, that kind of thing. But it doesn't necessarily need to know.
So those are types that are also defined. So if I just said F32
F vector, yeah, F32 vector, D vector, you'll see some D matrices coming up really quickly. All right, so now, this is the cool thing. If we look at Z, like I said, Z doesn't have the value 3 in it. It's actually a mathematical expression. And so Theano actually has this cool thing called pretty print, PP. And if you print pretty print, it will actually say that Z is actually the expression x plus y. That's all it is, which is really cool. All right, so example time, matrices, same deal. I've just switched out scalar with D matrix, and the same thing. We're going to add it through here, and this is a good example. So all I'm doing is exactly the same thing, and I'm just overwriting the variables x, y, and z now. And if I create some Numpy arrays, and you guys are cool with that, right? So let's see, we can go insert a cell here below, and if we type NA, So we get just a quick little 2x2 matrix, 1, 2, 3, 4. And if I call this function blorch, it adds them together. Most operations are element by element, but Theano does support things like dot products and matrix multiplications. But if you just take two arrays and add them together, you're going to get the element to element. If you multiply them together, it's going to multiply the elements together. And then, like I said, the different types. So V, F vector, V, and then you can do cool equation stuff. So let's get away from just adding two values together. Here we're taking the vector V, we're adding it to a square of itself. So I create a function out of this. I'm taking the V as the input variable. I'm returning R as it. And remember, so the key thing with Theano is just think about this thing as a description of some math. It's just, we're writing some equations. And now I can call it with a vector, an arbitrary vector, so I can easily do this. Notice that I don't care about the size. I could say 7, and blorch, it works fine. And it spits out that this is an array, the floating point type there. And bing, bada, boom, it just, adds the two things, or squares V first, and then adds it to V. Well, it adds V to the square of V. And so 1 squared plus 1 is 2, and 3 plus 9 is 12, and you see. All right. Okay, so now let's do a little bit more examples here. We're gonna get to a pretty complicated example in just a bit.
Just syntactically, is the function definition provided before making that function signature, and it's not like how you suppose you're used to with C definitions.
I know, right? So what, if I think I know what you asked is, this is kind of weird, right? With normal Python, you put function, and then underneath it, you put everything that's in the function, right? But here we're actually sort of building up this thing beforehand, and then saying, hey, the function is actually the output. It was weird. It's hard to get used to, actually, because the code looks weird too, because you do all this stuff, and then you say at the end, and I'm creating a function at the end.
But the thing is that tensor object has overridden all the mathematical operators, so that what it returns is a very fancy thing. It's not a calculation.
Yeah, it's almost like a fancy lambda.
Yeah, it is exactly a lambda thingy. Lambda is another functional way of doing things, and if you know lambda, this is exactly what this is. So again, it's kind of fun if we can do print Theano.pp R. Let's look at R right now. So remember here, you can actually see that, hey, it changes the 2 into a tensor constant, which is kind of cool. And then it knows the square. And so R is just this equation, right? It's just this is a cool equation. And these equations can be strung together. We're going to pretty print something that's going to blow your mind. So just watch out.
I noticed also it's doing type conversion, right?
Yeah. Yeah.
Cool.
So in NumPy, there's this thing called broadcasting, which says, hey, if I've got a matrix of one size and a vector that I want to apply to that matrix, NumPy will actually broadcast that matrix appropriately across if the sizes don't match. And Theano will do the same thing. It does a lot of figuring for you to make sure that it works out. But it's a stickler for types. So if you try to add a vector, if you try to add things that don't belong to be added, it won't. It will yell at you a lot. All right. Okay. So a taste of machine learning. So we've seen a logistic function before, and I'm going to show you a plot of this in before. But a logistic function takes a value and returns a value between 0 and 1. So any value of x from like -100 to 2013 will be turned into a value of 0 and 1 based on this function. And I'm going to show you a plot of it really quickly. And let's just do a quick, I'll come back and do all this kind of stuff. And I'm going to plot out something so you can see. Wait, where'd it go? Here we go. I want this. Boop. Right. There we go. So this is what a logistic function looks like. And we'll show you how I got that. Where an x value, the x value is the bottom of the graph, goes in and it has this nice little swoop. And we've seen this in machine learning before. It takes input value of arbitrary thing and then with either a 0 or a 1 or a relatively sharp fall off between 0 and 1 that is still smooth and differentiable. So this function is actually a neat thing, and it's used all the time in machine learning. It's basically a neuron decides, hey, I'm getting all this input value in my neuron. Do I fire or do I not fire? And that's what this function does. We're going to be using this function in order to make some decisions about stuff. And the way to build this in Theano is actually pretty cool. We say that I'm going to take a matrix as an input. So Theano is going to apply this logistic function on all the elements of my matrix. So if I have a 10 by 10 matrix, I'm going to apply that same function in every single one of those elements of that matrix. All right? And the function itself, well, except for the formatting of the code stuff, this actually looks like a mathematical function. It's 1 divided by 1 plus the exponent of negative x. And of course, if we did a pretty print on s, we'd see that, hey, that's what Theano is storing there. And we're just creating this and calling it a function. And then we're calling it logistic because that's our logistic function. So what I did here is I used NumPy. NP stands for NumPy. And this thing is a linear space. So this is a really quick way of just generating a whole bunch of numbers between a minimum value and a high value. And so I said, sample the start from -10 to +10 40 times. And you can see that this is the result I get out of it. Because it's 40 times, there's a little, it's not exactly right. And yeah, you can see it goes all the way there. And this is hard to read because it's negative. It's weird. But anyways, this is a nice way of doing that. Oh, wait. I mean, I'm sorry. This is the result of logistic. If I print out V here, let's make sure everybody's. There you go. It goes from -10 to +10. And then, once I have this input value, a whole bunch of an array, and notice that it actually has 2 brackets there. That's important because it has 2 brackets. This is a NumPy matrix. Theano expects a matrix. And I've made a mistake where if you send in Theano a one-dimensional vector, Theano will yell at you, saying, hey, I don't know how to deal with that. You have to make it a matrix because I expect a matrix and I really care. So you just have to pay attention to that. So now I'm calling logistic on that. And remember, Theano applies the function to every element in that matrix. So I take this and I produce this, where my values go from -10 to +10, and then the results go from something very small, 0, all the way to something almost to 1. If you plot that, you get this. Yay. All right, so far so good. Nothing too crazy. And in order to plot this, this little thing tells me to generate the plot inside here. And then this is matplotlib, which is a great little plotting program in Python. And then this thing says, take this value, use it as the x-axis, take this value, use it as the y-axis, and Bob's your uncle. All right. So far, so good. All right, so now we're going to come back to logistic. But this is, I'm just doing small examples to make sure everybody stays up to speed with this. Well, let's do some other stuff. Remember what I was talking about, parallelism and GPU efficiency? Well, now let's show you that you can actually do some stuff at the same time. So here, I create 2 matrices, A and B, and I'm doing some functions on them. And actually, I'm creating different math here, right? I create diff A minus B. Then I'm taking the result of that, and I'm creating an absolute value of diff. And then I'm taking the result of diff, and I'm squaring it. So I'm actually creating 3 different things. And absolute diff requires this to be created. So let's do a shift return on that. And let's try this. Insert put up. Let's do print Theano.pp abs diff.
Oh.
Okay.
Yeah.
Oh, Theano, thank you. All right. Oh. Oop. Ah, what did I do?
Yeah.
Oh, now I hit a. Sorry. There. So I love the fact that this printer knows how to do this. See what I did? I created A minus B and then abs diff, and it even knows that that symbol is the mathematical symbol for absolute value. So it knows that this and that are the same, and it actually builds this thing. So one of the things that goes on with this, you can create some really complicated math with this. And Theano, just as a pause here, Theano has all the standard mathematical functions, tan h, any cosine, anything that you want defined. It has loops. So you can have a sum function in math, if then else statements. So you can have if this, that, and any kind of thing that you would expect in a mathematical equation is almost implemented in Theano. So it's a very complete set of things. So once you know Theano, you can start looking at a SIGGRAPH paper, and you see this math equation, you go, oh, wait a sec, I could just type that into Theano, and then I could have it be executed. It doesn't become like, oh my gosh, I got to figure out, I got to get eigen to create a matrix, and then I got to do it all. You could just type the math into Theano, and it's not quite that easy, but it's getting really close to being that easy. All right, so now when you run this, there's something happening here. Look at this. I've got the A and B. Remember, this is the inputs and the outputs. And if I'm running this, I'm actually creating 3 different outputs at the same time, and Theano knows about this. So when it goes off to C++ and writes that C code that it's going to be executing whenever you type F, it is realizing that some of this stuff can be done in parallel. And some of the stuff has to happen first, like this diff has to happen before this can be computed. So Theano tries to schedule and parallelize stuff as much as possible. And while I don't have anything here that's going to really hit my CPUs, when you start running Theano, have a CPU monitor going, or a GPU monitor if you've got NVIDIA going on. It will slam your GPUs. It will light them all up, and it's pretty darn good about getting things parallel going. All right, so to run it, you can see that I'm sending it A and B. So A is this matrix, 1, 1, 1, 1. And then B is this matrix, boop, boop, boop. And then it produces 3 matrices out of here. It just prints a little weird. So A minus B is 1 minus 0. That's good. 1 minus 1 is 0. 1 minus 2 is -1. Perfect. And then abs diff of that, well, that's that. All the negative numbers went away. And then squaring it, well, there's the only thing that really squared there. So ta-da! Okay. Now, you're thinking, okay, functional gets you only so far. But it would be nice to actually have a state. And so this is the other cool thing about it. Boop, I hit return. State. We're actually going to be very blatant about our variable names here. So Theano, from one call to the next, doesn't naturally store things in those variables. Those variables are just math. But here, we're saying, hold on. I want Theano to know about something that it stays the same each time, or that it can always go back to it. But you still do this in the math side of things. You're describing it as saying, hey, this thing is a piece of state that I want this function to have. For instance, this whole thing is like, how do I create an accumulator with a Theano? I want to, each time I call this function, I want to add something to a value. Well, I create a shared variable, and then I do a input variable, and then where's the math? If I do this, there's no equation here. Well, with the state, you have to go a little bit different. So check this out. Here's the function, and here's my input. I'm going to use this variable as my input variable, and I'm just going to take a scalar. This isn't matrices right now, but just a scalar. And I'm going to return the state. Well, that's that variable. Okay, so far so good. But how do I get the value in inc to state? And that's you're reading ahead. There is another variable in the function call called updates. And what this does is it says, okay, this is what I'm going to do to my state variables. And you can supply a list of things here. It doesn't have to be just one thing. You can have a whole bunch of state variables. But this is where you say, hey, do stuff to the things that I want this function to remember about, or this shared memory that I'm going to continue to use. So what I'm going to do is take the state variable and I'm going to do this to it. I'm going to take state and add increment to it and then put that value back into state. So this is sort of like a little input-output kind of thing similar to this, where this is the thing that affects, this is how the state is going to get changed. So to run this at the very beginning, since I've only hit this once, if you say state, you can actually get its value. If I typed inc.getValue, I'd get an error because it's not, it doesn't have a value. X or inc or X or Y or all these other things, they're just math. But state now has an actual value associated with it. And then I can run a cum, and notice it returns a 0. That was kind of weird. Well, no, it isn't, because this is the input is 1. I'm going to return the state. Well, the state's value is 0. But then after I'm done with that, I'm going to also adjust state. So if I then hit state.getValue, it returns the value that's the thing that got updated. All right? So far, so good. So now, just a quick thing, you can kind of see, okay, well, now state's 1, so it returns 1. But if I do it again, the value of state is now 101. So this state gets updated all along. And here's the cool thing. Because state is a shared value, it floats around. Other functions can share it as well. So here, I'm creating a decrement function. And it takes the increment value, that this variable thing, and then the shared variable, and it does the minus sign instead. So I can hit return here, bloop, and then I get decrement, and it returns a state because the state is the same. But then if I print state, 91, it got changed. It got decremented by 10. So this state concept is very important. And if we've been talking a lot about machine learning and stuff, and you can think about this in terms of building machine learning kind of thing, where you have a whole network of equations that are updating your neural net. But inside your neural net, you have all the weights. Remember all those weights and biases on each neuron? Those are the shared variables that then the functions are continually massaging as they go on. So the way the neural net works is described through math, but the states are there representing the internal state of the neural net. All right, so let's do this. Here's our first real example that combines all this kind of stuff in it. Yeah, this is a pretty good thing. So the idea is logistic regression. What we're going to do is we're going to assume that we have a whole bunch of data points that are classified as either 0 or 1. And the data points can be n-dimensional data points. For instance, say I wanted to, in this example here, say I had a list of all the cities in the world, and associated with each one of the cities is their latitude and longitude. So you describe a city with the latitude and longitude points. So every city has 34,27. That's their latitude and longitude. And we're going to classify each city as either greater than 1 million people or less than 1 million people. So if a city is greater than 1 million people, it gets a 1. If it's less than 1 million people, it gets a 0. So now, can I build a function that, given a latitude or longitude, gives me a good estimate of whether it would be a 0 or a 1? Can I fit that data with this logistic function? It's a kind of contrived thing, but this is what's going on a lot in machine learning. All right, so let's do this. We're going to build this up in steps. So do the import numpy tensor, and then I'm also going to create a random number generator because we need to start things off. I'm going to have n, in this example, cities, so 400 cities. And instead of latitude and longitude, I'm going to use latitude and longitude and average temperature and all sorts of stuff, or whatever values that I'm interested in. And then I'm going to randomly generate a data set. So this is super contrived. This is coming from the Theano website. So what we're doing is creating n cities, and each one of those cities has a 9-element vector that describes them somehow. Latitude, longitude, you know, whatever. And then I'm going to create n integers, and they're going to have either a 0 or 1. This is a random integer between these two values, not including that value. So this is going to be that. And then we're going to say training steps is 1,000. And so let's look at B. It actually prints out a lot. Is 400 rows by 9 columns. And so this is a 9-element array that describes the location of a city or a piece of data. And I've got 400 of these. And then I also have 400 ones or zeros. Is the city greater than 1 million or less than 1 million? Greater than 1 million or less than 1 million, or whatever, however you classify these things. It's a very simple problem. All right. So now we're going to declare the Theano variables, x and y. Notice D is a matrix. This, y, is a vector. So x represents the 400 sample points with 9-element vectors on each. And y is the value of 1 or 0. So 1's a matrix, 1's a vector. Then, and notice, we'll go up here, see this, there's 2 brackets on the end of that. There's only 1 bracket here. So this is a NumPy matrix, this is a NumPy vector. Okay. All right. And then, remember I was talking about the weights on our graph? Well, the logistic regression has that weights. So I have my weights that I'm going to create as a shared variable. And this is kind of cool. I'm going to use this to initialize them. I'm going to create them, because this is a shared variable, I'm going to create a random vector of the size feet. So this is 400, 9 weights. And then I'm also going to create 1 bias. So this is just a single value of 0. We're just creating random values initially because we don't know how to fit this. And let's look at those guys. So here's our 9-element random numbers that are going to represent our initial weights. And then, of course, B is just going to be 0. Wait, did I run this? Oh, I never ran. There we go. Because if it didn't work, I was going to be sitting here debugging in front of you. Now, this is cool. This is the Theano math, right? And so, first of all, how do we do the sort of comparison? Well, the way this, we're not going to have time to explain the logistic regression, but some cool things, like if I want to take W, which is a vector, and X, which is a vector, and dot product them together, or no, X is a matrix. P dot X comma W, that will produce, actually, X is, right, yeah. And then we'll add B to that, and this gives you a value T. So this eventually reduces down into a vector.
Sorry, X the matrix?
X is the matrix, yeah.
And I don't know what the dot product is going to make.
Dot is just a vector, you're just multiplying this down. So the results of this are X is a 400 by 900, or a 9-element matrix. W is a 9-element vector. And so this is going to produce a 400-element vector. And we're going to add B to each one of those elements.
Dot is super shitty term for this.
Dot is matrix. So, you know, you can do matrix to matrix. Yeah. This is agreed. Agreed, but it is standard actually. This I've seen this in other places. Theano did not. Yeah, NumPy does the same. Yeah. So this is. Do not blame Theano, but I agree. It is a little confusing. All right, then. Remember, this is our logistic function. We just saw that there. We're going to apply that to every element, right? Then, this is kind of cool. We're going to clamp it. And remember, this is a little vector. And everything. This is a little vector. This is going to be a little vector, right? It's whether or not each element is greater than or less than 0.5. So here we're actually saying, I don't want that slopey thing. I want it to be either 1 or 0. And so I'm going to just clamp it. I'm going to say if it's greater than 0.5, it's 1. If it's less than 0.5, it's 0. Now this, whatever, this is a great big expression that does cross entropy. And I don't want to, I only have 5 more minutes, so I'm going to just skip over this. But this is a way of comparing whether or not the results we got are close to what we want. And so look at that. Y is a vector, and we're going to multiply each element of y by the log of P1. So log sort of emphasizes stuff. So we're basically saying, are these two the same? Or is 1 minus y times this the same? So it's basically a way of comparing whether the results that we're predicting are equal to the results that we want. And this is a nice way of sort of reducing the noise of this. And then finally, we have to reduce it all down into a single value that we want to make smaller. And so we want the cross entropy, the mean of the cross entropy, to be as small as possible. And we also want to make sure that our weights don't get too big. So we don't want the weights to go crazy. So what we're going to do is square them, multiply them by a small number. But we're going to, this is basically saying, make sure that this cross entropy is as small as possible while still making sure that the weights don't get crazy big. Because if the weights start getting crazy big, then cost is going to get crazy big. All right, so we're going to hit return here. All this is doing is producing this crazy math, right? And then, this is the best part about Theano, or one of the best parts about Theano, is because it's all symbolic math, you can do this. Take the gradient of your math. You can actually do automatic differentiation of this. So you can say, I want to know how my cost function changes as I change W. Or I want to know how my cost function changes as I change B. So this is just a Python convenient thing. It's saying, do the gradient of cost once with respect to W and once with respect to B. And I'm returning two other equations here. These are actually symbolic math equations that give you what happens to cost when you change W and when you change B. So let's try that. We're going to actually do this. And like I said, you want some pretty printing. Large. Here's your math for cost. And I'm not going to go through this. Obviously, the tensor constants are the big things that are filling this up. But this is taking all this math and figuring out basically a graph. It's a description of what that math is after you do all the stuff to it. And notice, there is, inside here, well, actually, the prediction isn't being used inside cost. Prediction is for another thing. But all this stuff is being computed, and then you can do pretty print on DW. Oh, yeah. Oh, yeah, this is so sexy. I can't stand it. Look at this. This is the math for the derivative of cost with respect to the W parameter. And W, remember, is a vector. So this is a gradient thing. This is telling you how cost changes as you change any one of the elements of W. So cool. And you could do it by hand, but why would you? Because we're living in the future. So now we're going to create two functions. One is the thing that actually solves this. And notice we've got our inputs, which are the locations of our cities and whether they're greater than or bigger than, or smaller than or bigger than 1 million. And then our outputs are the prediction and the cross correlation. And the updates are the key thing. Here we go. We're going to take the derivative of W, multiply it by a small value, so we don't change it too much. We're only going to change it a little bit. And we're going to change W based on this. And we're going to call this thing over and over and over again until W stops changing and B stops changing. And then this is just a little function that calls our prediction thing and says, hey, given the values of W and B, what are the outputs now? So let's do it. Let's hit shift. Have I hit? Yeah, I got that. So let's hit shift return here. And then we're going to do this. And notice, I'm going to do this over and over and over again. I'm going to call train over and over and over again with the same data. And it's every time it's going to do this, it's going to adjust W. And the neat thing about this is kind of a nonlinear problem. And so you're kind of, as you get closer to the solution, your W's are going to change. And this runs for a little bit, but it's not that. I'm only doing 1,000 training sets. And we can print this out. And this is kind of weird. Blah, it gives you the final model. These are the values of W and the values of B. And then here's the target values, and then you can't read that. So what I did, I'm going to really quickly, because we're running out of time, I took this exact same code and I put it into a little function. So here this is a logistic regression function. Now we've kind of gone off the code in the website, but It takes the input values and the target values and the number of training steps. And it's the exact same code. I'm zipping through it. And then I went to Wikipedia, and they have a really clever example of how to think about logistic regression. Say I have the number of hours a student studied and whether or not they passed or failed the test. So if you studied half an hour, you probably failed. But if you studied 5.5 hours, hey, you passed. So this is a sampling, and we want to see if we can fit that with a logistic regression kind of thing. So here, I'm going to define that, and then I'm going to do a little plot. So there's my plot, number of hours, and whether or not, instead of cities and population, we're doing number of hours studied and whether or not you passed or failed. And you look at that and you go, well, okay, I think maybe there's a trend here, but can I actually fit this with some data? So I'm going to run this logistic regression on this 1,000 times, and I'm going to get my model out, and here's the input values, and here's the output values. But that's hard to see, so we're going to plot it. Look at me, I've got all this stuff going on. And there's my original data, the red dots. Here's my logistic regression function, and here's the result of clamping it. So there is a thing that says, look, if you study less than 2 2/3 hours, you're probably going to fail. But this seems to be the sweet spot. Studying just a little bit more, and you're pretty guaranteed to win. Don't do this. This is silly. But right around there, that's a good thing. All right, one last taste. This is actually the last thing I wanted to do. Is beyond just cosines and squares and pluses and stuff like that, Theano also supports neat things like loops and if-then-else statements. And I put together a little thing like if-then-else statement. So here we have 2 scalars and 2 matrices. And there is an if-then-else statement and a switch statement. And the Theano guys actually made a point about telling you about this, because the if-then-else statement says, I'm going to evaluate this and then return either this thing or this thing based on whether or not this is true or false. If it's true, I'm going to return this. If it's false, I'm going to return that. The cool thing about this, and the reason this lazy is there, is because Theano is lazy about evaluating this. It will not evaluate this. If this is if it's expensive to compute, say the X is a 1,000,000 by 1,000,000 matrix, computing the mean of a 1,000,000 by 1,000,000 matrix is expensive. Theano does not compute all of this if it knows it's going to return this. And that's one of the cool things. It actually does lazy evaluation. That is not the case with Switch. Switch is more powerful. Switch can be controlled with a lot more information about it, but it evaluates both sides in order to do what it needs to do. And so if you can, use if-then-else, or if-else. But if you can't, use Switch. You just know that you're going to be paying a price for using Switch. And the cool thing is, you can put if-then-else statements inside things and ask for the derivative of it, and it will figure it out for you. So cool. So in this case, we're doing a quick little thing where we create A, B, and X, Y, and Z. I create my variables. I create a single equation. Z lazy is equal to if A is less than B, return the mean, else return this. And then we run it, and you get the value out. And we're getting kicked out. I'm going to ignore this just momentarily. But that's it. Thank you for paying attention. I'll put this on GitHub. Go to theano.org or whatever it is. Just Google Theano and you'll get the documentation for this. Super cool. And when you run it, it'll slam your CPUs, or you can throw it on the GPU without knowing anything, which is awesome. That's what I like, not knowing anything.
You still have to write down the regression functions, right?
Right, but it's so much easier.
It's easier. Yeah.
You don't have to think about writing it on a GPU. Well, you do have to think about it. You have to say, okay, shared variables and that kind of stuff. But
It's a framework.
yeah. How awesome is that?
Is there an overhead to where like you have to be doing enough stuff to make it worth using it?
Totally. Yeah.
Like you can just use it for really simple operations.
No. But yeah. But it only does that compiling once. Right. So it caches all that stuff. Jonathan Gerber asked, hey, if it's compiling something, can I use that? Can it create a library? I don't know the answer to that. It probably is creating an object file somewhere, and you might be able to link to it, but I don't know how to do that.
this the Mary Stacks meeting?
It is.
I swear I accepted and it's not on my calendar.
Oh.
I'm Ray Stacks, by the way.
Oh, hey, I'm Allison. Nice to meet
Nice
you.
to meet you.
So you're in town for a couple weeks then?
For 3 weeks, yeah.
Okay, I was like, how did I get that wrong? I swear all of them were up in Vancouver.
Yeah.
No, that makes sense. I was excited with only booking one room.
Yeah, and it's weird
Yeah.
because I don't know whether I'm officially on Mary or not. I mean, I'm billing it.
You are. You
So-
are.
Okay.
Where is it?
Yeah, definitely. I can't remember what your start date was, but you are.
Just a little bit.
Yeah.
There it is. Stop project.